Ladies and gentlemen, moving on to our next session. Our next session is a topic about organ on demand when your body is printable. Wow, this sounds very interesting. On this session, we do have Kun Pattara Nutaporn from MIT Lab and Futuristic Research Cluster of Thailand. He was joining us the previous session and he is still here. Next, we do have Kun Chetha Pankreabut, co-founder, Medically. He's joining us here. And the moderator for this session is Dr. Virasak Sura Leungchai from King Mongkut University of Technology, Thonburi. Ladies and gentlemen, please welcome our two panelists and the moderator.
Okay, thank you very much. So we see Pat again.
Hi, I'm back.
But the last session he talked is about the food.
Right, the food of the future.
So this session is organ.
Right, we're gonna eat the organ as well. No.
It's not going to be kway chap,
without the organ.
Right. Okay, during the way another panelist, Dr.
He's coming,
Chetha, he's coming. I think he's in the other. Sorry.
He's coming.
Right. Okay.
Right.
First of all, I think we should introduce our panelists. Start with the Pat. So last session you talk about the food. Today, this session you are going to talk about the organs, particularly printable organs. Okay, let's start with how experience you involved with things.
Yeah, so this panel is on organ on demand, right? So before I joined the MIT Media Lab, my previous position was at the Biodesign Institute at Arizona State University. The term biodesign already suggests that humans use biological material for design purposes. Like printing is one of them, right? But there are many more applications. Like you can use bacteria as well as for sensor. You can use organ on chip as a kind of a platform for monitoring and drug experiment. You can use microorganism to produce electricity. All of these are a kind of biodesign, right? The use of biological material as a design material. So there, I work a lot with bacteria and uranium, and then later on the idea of citizen science. As our speaker was talking about biohacking is definitely fascinating. One interesting thing about biohacking that's kind of related to this is that it's more like a bottom-up movement where, people start to have this, 3D printer. Recently I went to the MIT Media Lab Bio Summit and I saw people start printing the cell in their garage, like when Steve Jobs invent, Apple computer, right? So this advanced biotechnology stuff is not just in the lab anymore.
So from the cell, it's going to be the organs. It's got to pass through what we call tissues.
Right.
So it seems to be a very complex things. I remember that in June 2011, we have the first synthetic organs that came from the patients, the what they call windpipe cancers.
Yes.
So they can grow up their own cell and transplant it, and it's work. But in such a windpipe is very simple. Right, the air ducts.
Right.
So it's not difficult, but the people or the technologists or scientists, they imagine more and more things like the kidneys,
Or the heart,
liver,
right.
even the heart.
Yes.
So how come they can reach to such things, particularly with the new technology platform like the 3D printing?
Right. So so to print a cell is not difficult, as I say. People already do it in their garage.
Yeah.
But to print a complex organ, that's another story, right? Because an organ is made up of different types of cell and also different type of connecting tissue that control those cells to behave in certain way. So in order to kind of 3D print those complex organ, you don't only need to kind of layer on cell on one layer on top of another, but you need to engineer the way that these cells talk to one another. For example, if you look at the heart are made of like many type of muscle and tissue, and it's not just stick together. There's a signal that trigger one type of muscle to start, and then the muscle send another signal to another muscle, so the whole thing can kind of operate as a whole piece. So I think the challenge for bioprinting right now is not on the architecture level, but on the communication level between cell within the organ. How do we make all of the cell talk to one another? I think that's one of the challenge that people are working on right now. So yes, that is the thing that you need to do to move up from the tissue to the organ level. Right.
So, which organ you think is going to be the first one which can be printable?
Yeah, that's a very good question. Our coming soon, our future panelist, his company work with bone printing, right? Which is an important structure, because if you don't have bone, then you cannot walk, and if you have bone damage, then it might change your lifestyle. So his company work on bones printing, right? Which is a very interesting. I hope he can come and give us a presentation on that. But I think after we move from bone to another organ, I don't want to say which one is going to be the next, but I would say what is going to be the last. I think the brain would be the last organ that we can print, because it's not just the structure, not just the communication, but also the organization of neuron to create knowledge and memory. So brain printing, I think, that will be the last thing that we
why
can
we
do.
want a new brain?
Why would we want a new brain? That's a good question. Oh. Oh, okay. All right.
so we discuss the other panelist coming.
Oh, he's not coming anymore.
He's coming, I think.
Oh, he's coming?
Right.
Oh, never mind. Well, why do we need another brain, right? Well, because when someone is missing, we want another brain to help us, right? Right now we are missing one panelist, we miss one brain, so that might be the reason we need another brain. But I think if we think about it seriously, our brain degrade over time, right? There's a brain disease like Alzheimer and all kind of disease. If we can kind of reprint the brain and use it to replace the one that's already degraded, that might be a way that we could cure some of those complex diseases. So
last to say we want a new brain, but why we want to make such organs to transplant to the patients, right. And how the technology can, in terms of the medical technology,
right.
that the things, the organs, it can fit to the patients. How come to
right. Yeah, as you said, I think it's important, if we have an organ, if we have a 3D printer that can print an organ, the medical procedure to kind of implant that back into the human body is also a challenge. So I think the way that people have experimented in the past is that they try to culture the cell from the person and use that as the base material for printing, and that kind of lead to what we call, cell culture on chip, which is like the first step before you can actually print it. You need to culture the cell. You need to have enough volume of the cell in order to kind of put it in the structure that you want. I would like to point out this. You point out something very interesting about why would we have another brain, right? When we think about organ on demand, I think we should not just think about biological organ, but also a digital one. What I say is that if your leg is destroyed, one possibility is that you can kind of 3D print your leg back with the cell that you had. But there's also a people like Huge Her at the biomechatronic group at MIT that you not only use his leg to as a material for design. He also used like digital device and all kind of materials not limited to biological to kind of create a new one, a new type of leg that he can use. So biological augmentation through digital is also an interesting thing that we should consider. And with that, I think it open up, a new possibility, not just, bioprinting. Yeah.
That's the other things. The other technologies, for example, the synthetic biology,
Yeah.
making new organs
Right.
new organs, or something like the let's say biomimics,
Right.
or mimic the organ,
Right.
certain organs that the patient need.
Yeah.
Can you compare about this?
Yeah, biomimicry is big too. I think when we look at everything that we does in terms of using biological material as a material for design, we can look at synthetic biology, which Dr. Park Poom gonna speak on it later. Synthetic biology is one where we use DNA and biological information to alter the biological process. We also have biomimicry, which is using just the concept, the engineering of the biological organ as a blueprint to kind of recreate a new type of tool that we can use. So I think we should really think about what is good for what application. For example, when I talk about Huge Her, his leg is augmented. Oh, yay!
It's coming.
Yeah. That's
Okay.
awesome. สวัสดีครับ
I'm sorry, just rushed from the other session.
Yeah.
Really sorry about that.
Okay, you finish that
Yes.
one. And then
Yeah,
you
so
can-
so I think what I was saying is that biomimicry and bioprinting can go hand in hand. You can mimic, the biological structure from an organism, and you can kind of use it, through biological printing as well. So with that, we can-
So I would like to invite Dr. Chetha to introduce yourself and your companies, what you're doing, and in this session, the organ
On
demand.
demand.
So thank you so much. And again, I do apologize for being late here. So my name is Chetha Pankrabut. I'm actually a professor at the Faculty of Engineering, Chulalongkorn University. At the same time, I'm a co-founder of a company, a spin-off company from the university named Metically. So basically, Metically is a company that's using the 3D printing technology to help improving better life for people. So I would just take you a couple of minutes to go over what we are doing at the moment. So basically, we use the 3D printing technology to design exact same shape of the bone. So this is one of the organ that is very important to us. So using the 3D scan, 3D imaging, we can actually get the exact same shape of the bone. We can use that input to design what is going to fit your body exactly. And then we print it out using 3D printing technology. So this is something that we print directly from metal powder. So we use a laser to melt the metal powder layer by layer, and we create one piece of titanium bone. By having that, we have a qualified production line, so we can create something that is very, very good for health, and we get just Thai FDA right now. So once the doctor uses it, it's very easy for the doctor because you can design it really exact to the bone of the patient, and we can design some tools that the doctor used to make the surgery easier. And then the doctor can put that into the body and evolve from the data to the titanium piece. We can use only 2 to 3 days. So it's really quick, and that's what the doctor really wanted because the patient cannot wait for a long time. So what can we use this technology for? So if we focus only to the bone part, we have a lot of bones in our body, and we can use the technology to any kind of bone. But right now we're working on something that is kind of easier because it's the upper part of the body. So basically it doesn't take a lot of loads. But if we can continue to develop these things, so we can actually expand to something that taking more load, for example, the lower part, hips, for example, or knees. So I think that's gonna summarize what we are working at Metically, and basically how 3D printing technology can help printing bones.
So I go back to the same question with the Pat. So we discussed about the some organs that is pretty complex. For example, liver, kidney, even heart or brain. Yeah. How come the 3D printings can do that? Can print? In your opinion,
I think this is just the beginning of printing something. So you can imagine that bone is very strong, right? So you want something that is strong as bone, for example, metal. So that's why we use metal to print into a titanium piece. But imagine that we want something else that is not bone, for example, liver or brain or any organs in our body. So we cannot use titanium, right? But the same idea is applying. For example, if you change the materials to something else, for example, if you change it into some kind of stem cells that can actually grow in your body. So we just print, instead of printing the organ, we can print the pattern for the stem cell. And the stem cell itself in that pattern can actually grow or manipulate itself into that kind of organ in our body. So this is just the beginning, but what I can see is that you can print anything. You don't need to print exact same shape anymore, but you can start printing some pattern, and it can actually grow like the nature gives the ability of the cells to grow in our body to be your organ.
I have a question for you. So right now when you print the new bone, is that exactly the same as the broken bone, or can you actually make the new bone actually better than the previous one?
Oh, I think that's a very, very good question. So I have another picture here. So on the top row is basically what actually the cases where we have the patients. For example, you can see that all of these are basically something that looks really similar, right? The top row and the bottom row, because we want to repress something very similar to the bone. But for example, if the bone itself is very fractured, for example, if you look into this one, so this is a finger. So if you broke this joint, so the only way that people can do right now is to fuse it. Basically means you cannot move that joint anymore. So basically, if you want to print something, you don't have to think about exact same shape anymore, but because you can think about the function of that kind of thing, not only about the bone, but the organ itself. So if you think about the ability of printing the function, you don't have to restrict yourself to the shape. So you're printing something like the hinge joint, for example, to repress that kind of joint. It doesn't have to be exact same shape, right? But it do the same job. Same thing for the organ, as I mentioned. You don't have to print the liver into a same size of liver, because if you can do something that is only the template for the liver to grow, it can do the job, right? And it can starting to grow. Or we can say that it's 4D printing. It's not just 3D now. It with time, so it can print something and grow at the same time.
Can you draw the pictures if we want a kidney? We know that the kidney is supposed to be a filter, isn't it? The filter.
Agree.
Yeah. How can we make it while 3D printing? Can you share us?
Yes. Well, this is a picture I found on the internet. It's not about what we are doing at the moment. But if you're thinking about the printing, like inkjet printer, for example, this is an inkjet printer, right? So you have many cartridge here. But instead of having a lot of ink, but you put that ink into something that you actually think about the cells. Our body is starting from cells, right? That's like something that we want everyone have. But we want our own self. So right now people think about stem cells. Stem cells is right now is quite big, huge event, because we can actually draw the stem cell from our body like skin. Right. And it's not just the skin that we draw it from our body, because the stem cell is like the mother of the cell, right? So it can give birth to other cells. So if we actually separate the cells to something that we want, for example, the liver or kidney, and we put into the printer, so it can print the kidney or liver or what kind of other organ for us, right? But I want to make some point here. So if you print exact same shape of that organs, So it's not about the shape, as I mentioned, is about the function. For example, we have the case with the children. So the children, you can think about the children. He or she has to grow, right? So if we print out the bone in exact same shape, so what's gonna happen? So that kind of poor kid has to come back to the hospital and change the bone every time he or she grow, right? So why don't we just think about something that develop with them? For example, right now we develop something like a distractor. So it basically move or let the bone actually grow itself. So if you think about the 3D printing for the future, don't think about the shape, think about the function, and if it can actually do the job and grow with our body size, then I think that's the real challenge, I think.
And when you think about the cell printing, sometimes the cell cannot grow by itself. You need to have a scaffold, right? That is non-biological. So how do you see the interaction between the non-biological and the biological piece in the printing process?
Yes, that's a very good question. Because right now we can print some kind of scaffold, the template for the cells to grow in, right? But if you think about it, if a very strong template or a scaffold, then there are some space taken by that kind of scaffold. So it's not actually the liver or the kidney that we have. Or it might even interact with each other, right? So create something that we don't want it to. So right now the technology is thinking about something that is dissolvable. So for example, it's actually strong at the beginning, and then it's starting to degrade itself. For example, polymer can degrade, right, over time. So if you have a template of polymer, I don't know, it can be any kind of polymer, right, that is safe to us, but it can degrade over time. So then the cells inside can actually grow and take in the place where it was the scaffold. So that's exactly what we wanted. So we want to find that kind of materials. Right now, people are working on many things. For example, in metals, we use magnesium. So if you have heard about magnesium, magnesium is the worst metal in the world in terms of corrosion. Because if you put the magnesium like in the seawater, it will corrode away very easily because it gives away the electron. But if you think about magnesium in our body, then it will corrode, right? It's a corrosion. We don't want it in our normal usage. But if we put it into the body, then at some point of time, it corrode away, right? So we don't have that magnesium in our body anymore. But people don't use it at the moment. They only use it in the lab. It's not about thinking and use it right away, because in terms of organ or healthcare, we need to think about the long-term effect of that kind of thing. Because magnesium corrode away, but it stays inside our body, right? It might be somewhere in our body, and no one knows what's going to happen. So that's what we want to know before we put into the real use.
So based on the amazing project that your company does, it's more like creating an internal organ, right? Like the bone or the thing that's inside the body. How about like the external part? Like if someone loses their leg or their hand, you also need to have the external part so that they can kind of use their hand to interact with the world, right? Can you compare the biological printing and like a normal kind of prosthetic, like the robotic one? What is the pro and con of each?
Well, I think both of them are good in terms of helping people. It's just a matter of function that you want it. For example, if you want to use the biological part, you cannot use a normal printer to print biological part. So you need something that is very, very clean. For example, you need to print in a clean room, and there is standard, a lot of standard for the clean room that you have to use the printer to print it. You have to test a lot of things before you use it. But instead of printing something and you implant it into your body, if you print something that is external use, for example, exoskeleton, then you can use a normal printer that can print and fit your own body, right? We now have 3D scanner, so if you put your hand into the 3D scanner, you're going to have the surface of your hand. So then you can design any kind of thing, right? We can design something that can, make our body better if we don't have fracture bone, right? But if we want something that is fit to us, don't think about just the healthcare, but think about something that going to help us in terms of the ability to use. For example, if you born with something with this disability, then this kind of thing, this kind of 3D printing can help them.
Do you think with this kind of technology we can eliminate disabilities in the world?
Well, I would say I like to see that day, but I think it's a long time to develop into that day. But I think everyone here want to see that happen, and there's many things that we have to do to go to that point. But I think we are in the age of technology, and if this is happening, I think I have no doubt about that.
All right, then I'll ask you a question.
You want to-
Yeah. Well, you talk a lot about the organ printing. Now I kind of want to move a little bit to the organ on chip, which is kind of like the cultivation of the cell before you print. And when you do organ on chip, you can also use it to kind of test it and do like simulation. Like you can do drug and all kind of thing. Your lab has done a lot of like DNA printing and are moving forward to this cell on chip kind of thing. Can you explain a little bit of what is the future of this area?
Yeah, but I'm really not going to piece of organs, but sort of the mimicking the organs, not made from cell or tissue, but mimic. Because, for example, when we're talking about the kidney, it, in my sense, is a source of a filter. So, what we really want to see to do, we want to test the toxicity of the drugs. We want to test the toxin, whatever chemicals that impact to the for example, kidneys or whatever organs we are interested. Yeah, in the future, we might think about the if you can print this organ, why not print
And then
on
use it to
shape,
test, yeah.
and test
Exactly.
it. Yeah.
I think you have a very good point. So the safety of this kind of thing is very important.
Yeah.
For example, if we want to use stem cell, it can differentiate into the cells that we wanted, right? But it can also differentiate into something that we don't want it to, right? So if we don't have a good standard to test the toxicity or the biological effect beforehand, so then it might look good in the lab, but when you put into the body, it differentiates into something like a tumor cell, for example. Then that's something that you don't want it to.
I guess that is your concern while you're printing the bone with the non-biological material, not using the bone cell.
Exactly.
Right?
Yeah. I think that's the start point, because if we starting from something that we don't know anything about it, then there might be some consequences that we don't want to see.
So in case of the bone cancers, can you replace or transplant the bone for the such cancers?
Well, right now, if there is anyone that have the bone cancer, for example, the bone tumor, the doctor have to cut it like a big piece of the bone. So right now, the only option that the doctor have is to use something called bone cement. So it is easy to shape into the size and put into the body. But right now with the technology, we can actually duplicate that too. So I have one example, I think, here. So on your left hand side, so this is the example of the bone tumor here. So this is called giant cell tumor. So it's growing into a bigger cells, right? So it is look big, right, in terms of the thumb here. So the doctor have to remove it completely to make sure that the tumor cells will not grow into other place. And then if they don't have the prosthesis here, then the patient cannot move the finger anymore. Right now, no company in the world making that piece. So if you happen to be that person, you either have to print yourself, or you don't have the finger to text your girlfriend about what to eat for this dinner.
Oh.
So that's kind of something that we heard up from the doctors. This is actually our first case that we're starting to develop. So we heard from the doctor that in this case, she doesn't have the option at all because there's no one making it. So we're starting to think about the technology to help her, and that's why we come up with the prosthesis here. So we 3D scan the other side of the body, so it pretty much the same, and then we mirror image. So it's like you do the mirror, right? And then we print it out. So right now we implanted into her body for 2 years now. And now she can actually write, she can actually text the message, and she can actually live her life again.
I'm curious because you say something very interesting. You say, if you don't have this technology, you may need to go and print it yourself. So based on that, when do you think we can start to see people start printing their organ in their house, maybe using your company 3D printer or something, but not using it in the hospital, but more in the personal environment or personal context?
Yeah, I think that's the future, the very futuristic. But I can see that coming soon. So I think I saw some movie that you go into like a big machine, and it's starting to heal yourself, right? Very, very specifically in the area. I think that's something that it is in my mind. So you're not. I don't think you're gonna print like your heart like in the printer and put into your body, right? Because that's feel like unself. But if you go into the machine, for example, and it's kind of like robotic, open up your body, right? And trying to print or repair. Think about repair. You don't have to print the whole thing again. You can just print a part of it or repair, right? In the body, and then cross up your injury again. So I think that's what I see in the future, not like print the organ, in my opinion.
So you think in the future we can make a human, a man, with the different organs on demand?
Yeah. Like in Frankenstein.
Yeah. Well, I don't know. I can see the technology can do that, but in terms of the regulation and standard, I'm not sure. We are really lag behind in terms of the regulation comparing to the technology. If you know about the technology that is being developed in the USA, for example, they have to pass on one regulation called US FDA, so Food and Drug Association. So basically, you need to pass a lot of tests to make sure that it is good. I mean, good enough or safe enough to be used. And if you're talking about develop a new kind of materials, it has to be tested for a very long time. So even though the technology right now is ready, but you need at least another 5 to 10 years to test that kind of technology before you being used of that technology. So to go to that point that we just talked about, to on-demand printing, I think we have the start of the technology. We can see that coming, but we need also have to work on the regulations and make sure that it's going to be safe when it is ready.
Right. I think this session is quite interesting, and there's sort of skeptical. Perhaps we can have some questions from the floor. Yes, please.
I want to ask you about testing because it's important. It's like a product, right?
Yeah.
You have to test it, and to bring it to market, you probably have to use accelerated test. Mm-hmm. So I want to pick your brain on how we can accelerate the testing of these prints or these structures that we're going to build. Having the scaffold itself is not enough because you need to make sure you test it, the built out, and then how it decays or age over the life of the patient. So if you can share those things. And the second question is, what is the 3 most likely organ that's next, in your opinion?
Wow, that's a very good question. For the first question, so I think the regulations right now is very, very being restricted. So for example, if you want to use titanium, in my case, you have to test many things. For example, the strength of the materials. You have to use the exact standard for the strength for the test. Also, the biological test. You need to pass on one thing that's called biocompatibility test. So in terms of that biocompatibility test, you need a list of it. For example, if the cell can grow or not, for example, or if it left with some kind of chemical that is not good for you, or you have to test on the sterilization of the materials. So there are lists of things. So if you want to pass on one standard, for example, US FDA or European standard, there are different kind of tests. It's overlap, but it's not exactly the same test. But if you're talking about something that is very, very new, for example, the scaffold that is being used and let the cell grow and manipulate, you need to test on something that is not human. So you need to test on it first in a lab, okay? Put the cells in the culture where it can grow and see the result. If it grows and you do it again and again and again and it's good enough, then you put into, the protocol has to be animal tests. So you have to put into a rabbit, for example, or rat, to make sure that it actually represents what you are claiming for. And if you have a good number of it, then you enter the third phase, which is called clinical trial. So that's human. But you're not like starting to sell it at that time. You're having a clinical trial because you're starting from a small group of number of people. And then if it passed the phase 1, then you enter the phase 2 with a bigger number. And then you pass and pass and pass. So if you ask exactly what kind of test, then it depends on what kind of thing that you are developed. If you are developed something that is substantially equivalent to something that is being exists before, then you have to pass on a very small list of tests. But if you are developing something that is very, very new and no one else in the world have done that before, then you need to pass on a full list of tests. Yeah. Well, if you're talking about the biocompatibility, basically the regulations say that you have to test the most difficult one. For example, if you think about the risk of having something to be, infected, you have to test that thing. So if you test for the worst case, then you're going to pass anything else. But in terms of function, basically they have to do clinical study. So when I say you have to put into the small group of people, then you collect the data. So you have to pass on, you need to apply something that is called standard, right? The test of your performance. And then the doctor, the third-party doctors, the one that is not being benefit with your product, gonna see the result and say, okay, if it checklist, okay, if it pass or not, then you're starting with a bigger number. In terms of bio, because everyone have different kind of, size and everything else, then that means you have a random number. So if you pick anyone to being used your product, then it's already be random. So it's basically not a linear test. It's kind of like random number.
And the second
back
question.
to the gentleman asked the next organs. Yeah.
Well, right now, the first thing, the zero product is bone, because it's not now being developed, not only in here, but some other places too. But I think the next one that's going to be used is right now, it's some organ that is not like the most functional one, just to test if it's good enough to be used. For example, I've seen some kind of news, printing ears. So this is kind of the good example of doing something that is not like the most difficult one, because it's, outside, right? But this is, in my opinion, just to test the technology. If you can actually print the organ, the moving organ.
So the external organ.
External organ, yeah. And then from that point, I think you can starting to print something that is most critical to our body. For example, I think kidney will be the next one. And the last one, I think really everyone wanted is, I think is heart. Sorry.
That's the brain.
Well, the brain itself is very, very difficult. So I think that might be the next one. Or maybe the last one, I'm not sure.
So I think we are running out the time. I have the last questions. You both can share. So if the next one, which is the function and the internal one, when it's going to be reality? When?
Well, I think you can see the real example within 10 years, but maybe not like a real product, but you can see someone going to do that in a clinical study within 10 years.
I would say within 5 years. Less. Because as 3D printing is accelerating, and as we see that, even in Thailand, you have an amazing company here. I think it's going to be very fast, and future is always faster than we thought. So.
Okay, thank you very much.
Thank you so much.
Thank you very much.
much.
It's a fun panel. Thank you.
That was a very fruitful panel. Thank you very much, our moderator, Dr. Virasak Sura Leung Chai. Thank you very much, Kun Shetha Pankrebut and Kun Pat Nuttaporn. That was very inspiring.